Hey, so being able to train RL in real time from a browser game seems to be an interesting problem, I feel. So we're going to investigate the problem of running reinforcement learning on just any application by using the Dino game built into the Chrome browser. All right, so if you're new to Dino, so Dino is just it's an example of a browser game, but like here's Dino. You basically have a little dinosaur and he can jump and he's running along the desert, and if he goes walks into a cactus or a pterodactyl, he dies. That's it, right. So, and then we've got like a score at the top right over here. The baseline I'm comparing to, there's an implementation by Nicholas Renotte where he is taking Dino and learning to play Dino using reinforcement learning. So what does he do? He's using stable baselines 3 with the DQN algorithm. He's using MSS to take screenshots of the browser. He's using direct input to control the browser, and he's using tesseract to detect when the game is over. So that's the baseline. He runs at about 2 or 3 frames per second on, like he's using a desktop computer, like big powerful thing like a GPU. I'm just using that MacBook Air. He trains for 12 hours, and after 12 hours, he's getting something around 200, 300 points for an average game. I'm training for half of that time and I'm getting twice as many points. So how do I do that? All right, so let's look at the baseline architecture for how we're going to use RL on a desktop application or game. So here we've got a target game. Now, in this case, it's Dino, but it could be any browser or game or any game at all, in fact, that will run on the desktop because we're not using an API to interact with it. We're simply taking screenshots using MSS and controlling it directly. So here we've got MSS to take screenshots. So this is a really nice application that can take screenshots quickly. It's cross-platform. So Nicholas was using it on Windows. I'm using it on Mac. I believe it runs on Ubuntu. It's pretty nice. This gives us a screenshot, which is the state. So remember, in reinforcement learning, we need to have the state, we need to have a reward, we need to have an action. So the screenshot is our state. So this is going to be like a tensor which has like width and height because it's a screenshot. It's going to have some like depth because we've got 3 color planes. We then take this state and we feed it through a neural network. Now, this Nicholas is using nature CNN, which is built into the stable baselines 3. But the architecture comes from the original Minaratel Atari games paper. So the nature CNN then now puts an action. Now, in the case of Dino, there's 3 possible actions. We can do nothing, we can click space to jump, or we can click down to like duck. Then this action is given to direct input, and then direct input can directly like press keys or whatever. And in this case, direct input is going to press the space bar if Dino jumps, or press the down key if Dino ducks, or do nothing if we're choosing to do nothing. And we also need the reward and the done. So that comes from tesseract OCR. So tesseract is from Google. It lets you use OCR. What Nicholas is doing, he's taking a second screenshot just of the middle of the game where it will say game over when it's the end of the game. And if it says game over, then he's setting done to true, and then the reward is a function of whether it's saying game over or not. So if it says game over, I don't remember exactly what reward, but like presumably it's a negative reward for game over. Otherwise, like maybe a positive reward if it's not game over. So yeah, so using tesseract OCR. So that's it. But of course, we've got another thing over the top of this, which is the RL algorithm. So Nicholas is using the stable baselines 3 implementation of deep Q networks, DQN. So what that's going to do is basically going to update the parameters of the neural network, and how it's going to do that is like it's going to take in the states, the actions, and the rewards, and then based on its algorithm, it's going to update the nature CNN. Now, it's also going to also like control like when are we going to like take a step in the environment and so on. Cool. So this is the baseline architecture which we're going to evaluate, analyze, and evolve. The first thing I was interested in is, so how does like PPO and DQN interact as far as like when does it call step? Like how often was the interval between these? And the same with reset. Because normally when we're using the environment, like not recording from the browser or using the browser, but when we're just using a normal gym environment, like it doesn't really matter when PPO calls step or reset because the environment is absolutely perfectly synced with the PPO and the DQN. So if DQN goes away and thinks about stuff for a while, we won't notice because we only the environment is frozen while the DQN is going away and thinking. It's not going to carry on. When we're using the browser, everything just carries on. If the DQN goes away and thinks for 10 seconds, our dinosaur is dead. And same for PPO. So I want to know what is the pattern and the timing of calling the step and the reset. So how to investigate this? So what I did is I created an environment. I just called my environment, and it's got like a step, and it's got a reset and a close. And what I did is I instrumented the step and the reset. Now I gradually added more and more things, right? So like, but the important thing to start with is I did this step times dot append time minus start time. So what I'm doing is when I'm running this, first I'm setting the start time to now. I'm running it here, right? So first I'm setting the start time to the current time. So time.time gives us a relative time in seconds from some, it doesn't matter when it starts, but it gives us a time in seconds from some time. So we record the time.time before we start our learner. So that's an arbitrary point in time. So maybe start time is like 10,000 or 10,123, it doesn't matter. We record that at the start. And then every time the learner, the PPO or the DQN calls step, we record that in this step times list. So step times is a list, and it's going to contain the relative time between the current time when step is called and the start time. So it's basically a list. The length of that list is the number of times step was called, and each value in that list was the relative time since we started the DQN or the PPO that we called step. And I do exactly the same thing in the reset, except this time it's reset times. All right, so we're recording every time the DQN or the PPO calls reset, and every time the DQN or the PPO calls step, and we can graph this. All right. So what I do is I create a couple of learners, like one for DQN, one for PPO, and then I have a for list over these two learners. So for each learner, we're going to run a certain number of steps, which I believe is about 6,000. We run 6,000 steps, and then we plot some graphs. So we plot a graph of the step times and a graph of the reset times on the same axes. And then we also do a graph of the step times with a histogram. Let's look at these graphs because it'll make more sense. So here we're learning the DQN. It's doing like 138 FPS for in the environment. I'm doing various delays and stuff. Right. So here we go. Here's our graph for the DQN. So the x-axis is time. So the whole thing, the 6,000 steps took 60 seconds. So like these are just like basically like the environment is just simulating some stuff. Like we've got a network which simulates taking some time, and we've got an environment that simulates taking some time. Like if we look at the step, we've got like if self dot delay, then we sleep, or we take a screenshot. And we've also got CNN. I think we might be using the nature CNN actually. Doesn't really matter what we're using, right? So here, the orange dots are every time we call reset, and the blue line is basically the calls to step. So like, there's so many calls to step that it's just like a single line, but like basically this is just like lots and lots of calls to step. So basically, what do we see here with the DQN? So at the start, the calls to reset are relatively close together. So at the start, the DQN runs a bit faster, and then presumably this is like, so I'm doing 1,000 steps of learning before we actually do any learning. 1,000 steps before we start learning the DQN. Like if we look at the configuration of the DQN, I've set the DQN. The learning starts as 1,000, right? So that is here. So basically at the start, before learning starts, then the DQ is running a bit faster, and then after that it's running a bit slower. But basically this is continuous, and this is noteworthy because we'll compare this with the PPO in a sec. So basically the DQN, we're continuously calling step, and then every so often calling reset. So basically I made this environment like end every 300 steps, like somewhere I configured it to end. So we're saying, all right, there's 300 steps per episode. So basically, we call steps 300 times. After 300 times, like the environment says, all right, you're done. And so we start a new episode. So that's why we've got this regular period between each of the resets. So each of these resets represents 300 steps. So we say that 1,000 steps before starting learning, so it would be 3 resets, right? So that's about right. I mean, it's going to be like 3 1/3 resets, which is about right. All right, so this is continuous. So let's compare this graph with the PPO graph. So here we're doing PPO. So everything's the same except we're doing PPO. And so here's the graph with PPO. So this is pretty interesting, right? So this is where it's doing the learning. This is doing it for rollouts. And then so it rolls out for something like 2,000 steps. Let's have a look. Yeah, 2048. So each rollout is 2048. This is set by the end steps. Like when we call it, we're doing end steps somewhere. It defaults to the end steps defaults to 2048. Right. So if you don't put an end steps here, that's going to do 2048. Like that comes out of the PPO default configuration. Right. So basically, when we do the PPO, it does steps, reset, steps, reset, steps, reset for 2048 steps, and then it stops. It stops calling the environment whilst it goes away and it does some processing. And during this processing, it's actually learning. This bit is not learning. This bit it's learning. And then we do 2048 more, and then learning, and then 2048 more. So this is kind of interesting. So all right, so like, how does this fit in with if we're going to do with a browser? So look, it doesn't wait until the end of the game. It's in the middle of an episode. It just like stops. It goes away. I think so. Obviously, our dinosaur is going to die at this point, and ditto here. So if we were to use PPO for the dino, then the dinosaur is going to die at this point. It's going to die at this point. So I wouldn't want to be using PPO like this if I am the dinosaur, because I'm going to die. With the DQN, it's fairly regular. It's just like constantly, except at the start when it's running a bit more quickly. So we might want to put some sort of sleep into our environment if we're doing the dynos to make sure that the time between steps is regular. For the PPO, there's not much we can do. Like we're going to get these gaps. Right now, what are these histogram graphs? So the histogram graphs is I took all of the calls to steps and I just plotted a histogram for often. So like we can see the histogram command, right? Histogram, step times, and then bins is the number of seconds. So like this is the total time. So basically each bin is 1 second, and the height of the bin is how many steps will run in that second. So this is the step frequency. So if we look at the Q learning, we can see at the start the frequency is higher, which corresponds to this bit, right? It's higher because it's not doing any learning. It's not taking any of the things in the replay buffer and learning from it. It's just running the rollouts. And then rollouts start, and then basically at that point it becomes fairly constant. There's a little bit of a somehow the frame rate dropped here for some reason. I'm not sure why, but that's interesting. Oh, where's the DQN is basically flat. Now let's look at the PPO. So the PPO is like this. So basically it's fairly flat. Now, if you actually strip out all of the delays from the environment, actually there's a little bit of a ramp up here. We don't see that here. With a normal environment where the step takes some time and the network takes some time, basically it's flat and then it drops to 0 while it's thinking and processing the stuff that's in the rollout from the rollout, and then it's flat. Cool. All right, so yeah, so this is the first thing I looked at was the timing. So I thought this was interesting to compare the DQN with the PPO, like to consider should we be using PPO or DQN. So this doesn't necessarily make the decision, but like this is some information to keep in mind. Right now, the next thing I wanted to look at was the timings for the MSS, because Nicholas said he only got like 2 or 3 frames per second, and it was strongly implied this was because of the MSS. So I thought I would measure the MSS. So what I did is I put into my environment MSS, and I've got this parameter grab ball equal false, and if we set it to true, every step we're going to take a screenshot, and the screenshot is going to be like grab width, like grab height, which comes from the initializer. Yeah, and then so that recording you just saw was for a width of 494 and a height of 128. All right, so I've skipped over a bit. Why 494, 128? Because Nicholas was a lot larger, right? All right, so here's one of my first tricks for Dino is when we run Dino, all right, Dino. It's giant, but we don't have to make it giant. We can make it a lot smaller. Okay, it's much smaller now. Right, and then how big is it? Well, basically we need this space here, which with these blue lines from the left border to the right border. So how big is that? So if I use the screenshot, we can drag that down and there's some numbers next to the screenshot. So it's like about 498 wide and 166 tall, approximately, like give or take a pixel, right? So yeah, it probably should be 498, not 494. Anyway, right, that's where I get my 494 wide. Why did I put 128 high? It should be 166 high. So actually in Dino, I'm actually using 166, I believe. 155. All right. Anyway, yeah. Actually, maybe I should be using 166. Interesting. Anyway, so I get this. So I'm basically doing a grab here if self.grab is true. Now those results you just saw, grab is indeed true. So we're actually doing a grab. We're not doing a delay, so we've also got like there's a time.sleep available here, right? If self.delay. Delay defaults to false, and where is delay? Oh, delay defaults to 0, right? And we're not passing a delay. So I'm not doing a delay, we're only doing the screen grab. But we're doing that every step. And if we look at the frames per second, we're getting 80 or 90 per second. This is while we're running, this is DQN, right? While we're running DQN, we're managing to get 90 frames a second, running DQN and taking a screenshot every step. Right, so it's pretty okay. And PPO, we're also getting 90 frames per second. And this is including running a network too. This is running I think this is running the nature CNN. Let's have a look. Is it running nature CNN? Yeah, policy equals CNN policy. This is running the nature CNN. So we're running nature CNN, and at the same time, we're managing to grab like 90 screenshots a second. So it's all right. Now, originally, it was a lot slower than that for me because I was doing grab.pixels. If you do that, this is really, really slow. But Nicholas isn't doing that. So the MSS, I think it runs quickly. Now, if you have a slightly bigger size, it runs a bit more slowly. So you need to keep the size down. But yeah, this is running on a MacBook Air, by the way. It's not a fancy computer. There's no GPU. It's just a MacBook Air. All right. So then the next thing I wanted to check is what about tesseract? Text recognition OCR. Is this fast? Well, let's check. All right. So if we go down here a bit lower, try tesseract timing. So install tesseract. And what I do is I take two different dimensions. So this is height, this is width. This is the dimensions Nicholas is using for his game over recognition, if I remember rightly. This is the dimensions that I would need if I was going to recognize game over in this smaller screen, right? This is like 27 by 228. Like if I put the screenshot over the top, it's like this is like 223 wide by 23 high. So like give or take a few pixels, it's 228 by 27. All right, so that's why I've got this. So this is what Nicholas is using, this is what I'm using. And then we measure the time for the screenshot, that's the grab time. And we measure the time to do the tesseract, that's the tesseract time. So we're doing high tesseract.image to string. And then we run this for the two different dimensions. I run it like several times, just in case it's like slow the first time and then faster after that. Because sometimes things need a little bit of a warm up. Like there's various caches and stuff. So I run it 3 times to be fair. So I've got 3 iterations. For each one, I get the time for the grabbing, doing the grab, and the time for the tesseract. And down here we've got the times. All right, so using Nicholas's times, The MSS time, the grab time, pretty fast. It's like a hundredth of a second. But the tesseract time, over a third of a second. This is why Nicholas is only getting 3 frames a second. It's not the grab, it's the tesseract. All right, if I do the smaller one, it's a lot more reasonable. It's like just under a tenth of a second. I guess it's like a 12th of a second. It's still pretty slow. So let's get rid of that. How can we get rid of that? Well, we're gonna have to find another way for detecting when the game is over. So the first like trick to get this to run, to get my performance, is rather than having Dino being giant, we shrink. And Dino conveniently shrinks everything for us, so that's great. The second trick is I'm not going to use tesseract, but what am I going to use instead? Right, so let's watch what happens. What happens when he dies? The screen freezes, right? When he's not dead, everything is moving. As soon as he dies, the screen freezes. So we don't need to be able to read this. All we need to do is look at, is the current frame equal to the last frame? Is the current snap equal to, is the current grab equal to the last snap? Now it's true we might slightly overshoot by a frame. Like the time when he dies might be like 1 or 2 steps before we tell PPO or DQN, okay, you're dead. Hopefully it can deal with that. Right. So that's my plan. I mean, that's what I did, right? I don't use tesseract to detect the end. I just wait. If we got 2 consecutive frames which are identical, he's dead. Right. So that's my second trick. That's because the tesseract time is really slow.
So the next change is not really about learning, but how to get input into the Dino application, how to press space, and how to control the mouse.
So I'm using pytorch GUI, not direct input. Why am I using pytorch GUI? Because I'm on a Mac, and direct input doesn't work on a Mac. I always had noticed other people in the comments on Nicholas's video saying, hey, you should use pytorch GUI because then it'll work on other platforms. Well, yeah, I mean, I have to use it on a Mac, right? But when I started running it, it was using a lot of time. Like every time I clicked on something, it took a tenth of a second. Like click on a mouse, click with the mouse, tenth of a second. Press the space bar, a tenth of a second. Now that's a lot, right? But if you go from Google, it turns out there's something called pytorch.pause. And if, the thing is, it is actually on purpose pausing for a tenth of a second after everything. If you set pytorch.pause to 0, actually it becomes a lot faster. Now, the last time I ran this, I'd already set the pause to 0, so you can't actually see the difference. But basically, you can imagine all of these zeros are ones with it, if it's not 0. With the pytorch.pause set to 0, now it's running. It takes about, I guess it can run about 50 times a second. So it's not incredibly speedy, but it's kind of okay. It's a lot better than the tenths of a second anyway. It is kind of a bottleneck, so it'd be good if we can accelerate that, but it's good enough for now. So this is what I went with. I went with pytorch GUI. I set the pause to 0, and this is kind of fast enough. Oh, one thing, something very important for pytorch GUI. It's going to move your mouse around, which means you can't do anything. So pytorch GUI has a fail-safe built in, which is really useful. Basically, if you just slam the mouse down into the bottom left corner, or no, any of the corners actually, but bottom right for me is sleep, so bottom left, slam the mouse into one of those corners, and it's going to throw an exception and halt your program. Obviously, that sucks if you're in the middle of training, which is why I'm using my other MacBook, because the other one's training. But like, it's really important to know that. So yeah, you run it while it's running. You basically can't use your MacBook, which really sucks. And or whatever computer you're using. And then if you need to interrupt it, you just slam the mouse into one of the corners. There you go. All right. So the next thing I wanted to look at is, so we looked at like how often is the DQN and the PPO calling step and reset. But what about how much work are they doing? How much work is the DQN doing in between each step, and how much work is the PPO doing between each step? All right, so what I wanted to find out was like how often is the network being called, right? So when we create the PPO, we're creating this CNN policy, right? This is instantiating a network. It's instantiating a convolutional neural network. It's instantiating the nature CNN. It's like a 3-layer convolutional neural network. How often this has been called? All right. So how to figure this out? So what I did is I created my own network called my CNN, and we do exactly the same thing. We instrument it. So whenever we call forward, we're going to record the time that we called forward into this net times list. So before we had step times and reset times, and now we also have net times. We're going to have 3, right? And then we run this, and then we see when is forward called. So we're going to see when is step called, when is reset called, and when is forward called. And we're doing this for both a DQN and a PPO. Here we've got DQN and here we've got a PPO. And we just add this in the policy quarks. There's a way of, in the policy quarks, you can give your own CNN class. So now down here, we've got results, the graphs. First one is DQN. All right, so the blue line we saw before is the step. The orange dots we saw before is the reset. And the green line, well, this is again, it's made of points. The green line is the points of whenever we're calling the forward of the network. Right now, for the DQN, you can see at the start, we're calling step, I mean, we call step all the time. We call step every so often, every 300 steps, right? At the start, we don't call the network, but then after 1,000, we start calling the network. Of course, this makes sense because we're waiting 1,000 steps before we start learning. So we wait 1,000 steps and then we start calling the net. Interesting. Okay. All right. Now, what about PPO? So PPO is down here. So PPO is a little bit surprising when I first saw it, and then it made sense more later. So we've already seen the blue line and the orange. So the blue line is recording the steps doing the rollouts, and then in between the rollouts, then it's going away and thinking, right? So we're going to expect a green line while it's thinking because it's running the network to learn, right? But actually, the green line is here the entire time. Now, why is that? All right, now we can get a clue if we also log the batch sizes. So I log the batch sizes too. We go back to the CNN. I am logging the net times, but I'm also logging the batch sizes. So in this batch sizes and time, I'm logging the time and the batch size. So now we can plot a graph of batch size against time. Right. So now we've got one other graph which we've scrolled past. Right. So DQN, all the time we've got 2 different batch sizes being called. We've got 32 and we got 1. Right. Let's just like make a note of that mentally, and then we're going to look at the PPO. The PPO also has 2 batches, 32 and 1. When it's doing the learning in between the rollouts, it's using a batch size of 64. During the rollouts, it's using a batch size of 1. So this is giving us a clue to what's happening. Right, so what's happening during the rollouts, this batch size of 1 is because during the rollout, it's having to follow the policy. To follow the policy, every time it makes a step, it has to get the current state of the environment, pass that through the network, batch size 1, get the action, give that to the environment to make an action. So basically, during the rollout, it's just using a batch size of 1 to do the rollout, to predict the next action. It's not doing any learning, it's just the batch size of 1. So these batch sizes of 1, these should be pretty fast because it's just very small batches, right? This should be fast. And then while it's doing the learning, it's using these batch sizes of 64, a lot of batches of 64, doing a lot of work here. At that point, Dino's going to die. Now, if we go back to the DQN, we have both of these at the same time, right? So it's the same thing, of course, right? The DQN is doing it at each step. It's doing a rollout, which is a batch size of 1. Okay, we're going to take the state of the environment, pass that through the network, get our action, take the action, and then the DQN is then going to take some more samples from the replay buffer, do a giant batch of 32, and do some learning on that. So the DQN is constantly learning all the time, and then the PPO is only learning in these bits here. Now, what do we want for Dino? Something to ponder. All right, which do we want? Do we want to have not much happening here while we're doing the rollout and then it freezes and Dino's going to die? Or do we want always something is happening all the time, which is going to like slow stuff down, but Dino's not going to suddenly die. All right, so this is just some DQN versus PPO. Right now, about this point, I felt I had enough like tricks or benefits or things that we could do to perform better. So I started to look into implementing Dino. So we're not using tesseract, so that saves us tons of time. We're shrinking the Dino game, so that's going to save us a bunch of time. I haven't mentioned this here, but I'm going to stack up the 3 or 4 previous time step frames so that we can detect movement. This is very standard. I'm not sure why Nicholas isn't doing that, because we kind of want to know movement so we know which direction dinosaurs moving, how fast wherever those things are, trees. I don't know, something's moving that Dino crashes into. Whatever is moving, we want to know how fast they're moving, because they get faster with time, right? I mean, they're not actually moving, it's Dino that's moving, but when we're playing the game, it looks like they're moving. And they move faster with time. So Dino needs to know how fast they're moving, because the faster they're moving, he's going to have to it's going to have to time its jumps differently. So that's the third thing I'm doing, is I'm stacking up frames. And then the next thing is, do we want PPO or DQN? So to start with, I kind of wanted to go PPO. I mean, I did go PPO. Why did I want to go PPO to start? Well, just because DQN is kind of usually hard to tune. There's a lot of things to tune. PPO seems it works pretty well, pretty fast, doesn't need much tuning. Why not just go PPO? Now, one challenge with PPO is like Dino dying, right? Like those gaps. So what do we do about this? So here's my idea. I mean, here's what I do. So change the reward. So one way of doing the reward is each time step we get +1, and the idea is to, I mean, I don't know why I'm going the whole thing. Like an episode is just one of these things between the 2 red things, right? Each time step we get +1, and then one Dino dies, he stops getting the +1, right? Or it stops getting the +1. Maybe she, I don't know. Now the thing with that is that then here Dino dies unavoidably. And then we come back online. We're still in the middle of an episode. PPO still thinks we're in the middle of an episode, but Dino's dead. And then what do we do? So here's my idea. Rather than giving +1 reward for each time step, I simply give -1 that reward if Dino dies. And if Dino dies because of PPO went off and stopped controlling Dino, we simply don't give the -1 reward. We just give a 0 reward. All right. So Dino just gets 0 reward at each time step, unless Dino actually dies, and it's not because of PPO's fault. I mean, it's sort of PPO's fault because PPO is controlling Dino, but like not because like PPO is just going away for like a few minutes and calculating stuff. Right. So that's what I did. I think that works okay. All right, so that solves these gaps. And then, but one advantage of DQN is the fact that it's sample efficient, right? So shouldn't we be using DQN because the game can only run 30 frames a second, and we used to be able to do like lots of frames per second? Well, there are 2 reasons why I decided that was not a reason to use DQN. The first thing is we're actually struggling to get up to 30 frames a second anyway. Like there's so much stuff going on, and especially I'm on a MacBook Air. So I actually can't run at 30 frames per second anyway. Like, even getting rid of tesseract and stuff, I'm only getting like 20 frames a second. So, and this is using PPO actually. So I really don't want DQN running and making things even slower. Like, basically, we want to be able to collect the data as fast as possible. We want to be able to run about the same number of frames per second as Dino. How many frames per second does Dino run? So I went over and Googled it. It looks like Dino is running at 30 frames per second. So ideally, we want to be able to also run at 30 frames per second. Now, I wasn't able to run at 30 frames per second, but I'm going to run faster if I'm using PPO than if I'm using DQN, I feel. So better to use PPO. So the next point I want to consider is, so let's say we have an action environment, and here is the actual Dino environment actually. And we've got this step. And in this step, we have to do a bunch of things, right? Like jumping and grabbing the screen and calculating the reward. What order are we going to do these in? All right. So let's think about this. So let's write down the things we have to do. We have to apply the action or run the action, let's say. I'm not sure how big commit is. And we have to grab screenshot, like get the observation, right? We have to predict the action, right? So the network's going to do that, like PPO or DQN as part of SBS3 is going to handle this. But it's still something we're going to have to do, right? We're going to have to decide the reward. I guess we can say calculate the reward. We have to decide if dead, determine death, done, determine done. Is there anything else we need to do? There is actually, but I'll come to that in a sec. Yes, we have to do all these things, right? This is going to be all inside the step function. Well, actually, it's not all inside the step function because the predict the action is outside of the step function, right? So the predict action goes sort of here, right? It has to go. I mean, we can either write it here or we can write it here, but either way, it's like outside of this function. We can either think of it as right at the end of the function or right at the beginning of the function, but we can't control it being outside, but we can control all of these things here. Now, something else to think about is we want to run at a certain frame rate. We want to run at a constant frame rate. If we remember back to when we were looking at like the Q learning, sometimes Q learning ran more quickly, sometimes it ran more slowly. We want to be running at a constant frame rate. What frame rate do we want to run at? Well, it looks like Dino runs at 30. I don't have definitive proof of that. It's just an impression I get from Googling around, but I haven't actually measured it. I haven't actually checked the code to find out what frame rate it's running at, but 30 would make sense, and 30 is kind of what people are saying. I'm going to guess it's running at 30. So we want to be running up there. On my computer, on my MacBook Air, I can get about 15, but I want to get a constant 15. So how to do that? So basically what we need to do here is we're going to have to insert a delay. Right, so we're going to insert the delay. And that delay is going to make sure that this loop takes exactly the time. So we're going to fix a frame rate. Let's say, actually, I'm fixing it at 15. If I had a faster computer, I might fix it at 30 to match Dino. I don't have a faster computer. I've got a MacBook Air. So I'm fixing it at 15. If my loop was slower, I would run it slower. I'm running at 15. So basically, we have to insert a delay that makes sure that that frame rate is exactly 15 or whatever frame rate we want. So we have to figure out where to put this too, right? All right, so then let's think about this loop. For predicting the action, we probably want the screenshot as close to that as possible, right? But at the same time, we probably want to calculate the reward and determine the done after grabbing the screenshot. These both can be done quite quickly. Calculating the reward is fast. It's just like if we died or not. Well, actually, so that one sort of depends on this one in a sense. Determining the done, we can do quickly now because we're just going to check, oh, is the image the same as the last one? If it is, we're dead. All right, so that's it. So these two run quickly. This one runs fairly quickly. Running the action, it makes sense to run the action immediately, right? Because we've predicted the action outside of the loop. probably the first thing we want to do at the start of this loop is to run the action, right? So we run the action, then we insert a delay, and then we can grab a screenshot and do all this stuff and go here. Right, now something to think about, and one of the reasons that pushed me towards PPO, not DQN, I mean, we could try both. They probably both work. Anyway, I went for PPO. I kind of felt it would be good to make this delay as long as possible so that we take the screenshot sometime after running the action. Because that means that the reward is now affected at least a little bit by our action. Now, actually, I thought about it a bit later and I thought, okay, in Dino, like, the reward is actually much later because you have to wait for Dino to jump, which takes a while, right? Like, it's not just like half a frame or one frame, it's lots of frames. So maybe that doesn't matter. Anyway, that was kind of my reasoning for going PPO. I decided I kind of want to insert a longer delay. PPO, because during the rollout, all it's doing is predicting the action. It's not doing any learning. Actually, I haven't double checked it's not doing any learning. Maybe it is doing learning. Not sure. I won't swear for sure that it's not doing any learning during the rollouts. But as far as my understanding is, it's just doing like a batch size of 1. It's just taking our screenshot, running it through the network with a batch size of 1, getting an action, and then we're going to run that, which is exactly what we'll do if we load the model later and we run the trained model, right? What we're going to do later is going to predict the action, we're going to run it, and then we're going to delay, and so on and so forth. So this is going to match our like inference time running the model. So yeah, so this is what I decided I would do. And so yeah, this was kind of like my final, like, okay, I'm going to do PPO. So this is what I did. So one question in my mind was, like, how precise can we get the frame rate? So what I did is I did the whole logging thing again. All right, so here I'm running at 15 frames per second. And then what we have here is we have a histogram plot. This is the time since the last frame. And then like this is some measure of frequency or whatever, right? I've got 100 bins. I'm plotting in the range 0 to 0.808. And we can see it's pretty good. Like, I don't know, I guess it's within 10% or something like that, which is not terrible. I mean, like most of them are in this one, right? Which is probably like, if you did like 1 divided by 15, it's probably this number. There's a few where the delay is slightly less for some reason, but then most of them are here. So I think that's pretty good. Yeah, so we're getting a constant frame rate. Yeah, so here's our step function, right? So right at the start, we do an action. So I'm only using 2 actions. I'm not using one. I'm not using 3 actions. I've just got like either press the space or not. Yeah, so if the time since the last frame was like more than 3 times the frame length, then we assume that the PPO is doing its learning bit. And so we just set done to true. And we're also going to completely erase the frame. We're going to fill the frame with 0. So that like we don't see so the model doesn't see like a game over at all. It just sees blackness. It's like, all right, blackness, I like that. I don't get any negative reward. It's good. This is just like a warning to myself for like when I'm choosing the frame rate. One thing I did at the start, which was stupid, is I was setting the so each time we're gonna store like this point in time so that we can then measure the time since then the next time to decide how long we're going to sleep for. Like here we're sleeping in order to like make up the rest of that frame, and the time that we sleep for is like our desired frame length, which is like 1 divided by the frames per second minus the time since last. Oh no, yeah, okay, yeah, sorry. The time since last is, oh god, this is already complicated. There's probably a simpler way of writing this. So the time since last is the time since like we stored the last step time. What I was doing initially is I was storing this before the delay, which obviously, well, it's not obvious, but it wasn't obvious to me. That is wrong. It basically means your time. It messes up your time. Anyway, you put the time afterwards, and you store the time afterwards, and then it will be correct. So as far as how I'm configuring SPS3, I've got learning rate 0.001. I'm saving every like 1,000 steps, but like I'm making sure that this is kind of a multiple of n steps. N steps is like the interval between each like sort of training run that PPO runs. Because if it's too small, like basically it will learn at the start, but later on when the dinosaur gets quite far in, then it's going to learn less well. And I put the FPS to 15. I'm choosing 15 because I'm assuming Dino is running at 30, and on my MacBook Air I can run at 20. But I kind of feel that like the FPS should be no, well the Dino's FPS should be like well anyway, so Dino's FPS is twice the FPS I'm using, like 15 versus 30, right? Whereas if I used 20, like I kind of feel like they wouldn't be exactly in step with Dino's frames. So I kind of feel 15 is better, but I don't know. I haven't tested. Maybe 20 would work better. I mean, they both learn pretty well. Cool. Yeah. So that's it. That's what I did. So I guess we could summarize the things I did. So shrunk the Dino game to as small as possible. Well, yeah, to as small as possible. Stopped using tesseract. We simply use compare last 2 frames. If same, then dead. Done. Stacking up last few frames. I think I'm doing I think I'm doing 2 previous frames in the current frame. So let's have a look. Oh, I'm doing 3 previous. Oh, no, I think this means 2 previous frames plus the current frame. Anyway, I'm doing n stack equals 3. I'm using PPO instead of DQN. I mean, maybe DQN works well too. I don't know. I mean, probably the fact that I'm not using tesseract anymore and the frame rate is just so much higher, they're probably both going to work better. Like maybe DQN will work really well too. I don't know which will work better because I haven't tried DQN. I like in my mind, DQN is harder to tune. PPO is easier. It seems to work. So just like, all right, let's just use PPO because we can. Oh, I'm using pytorch GUI because I'm on a Mac. Like this is cross-platform, right? MSS works great. MSS is fantastic. It's really good. It's really nice. And SPS3 obviously is really great. Oh, and yeah, OpenCV is really good. Oh, right. Inserting a delay. Constant FPS. I think this is really important. Like if you've got a variable FPS, and you also want to match the FPS with the prediction time, like when you're running prediction, when you're running inference, when you're loading the model and running it, you're going to want to run it at the exact same FPS. If you run a different FPS, the model is just going to be like, what happened? Like it's going to like predict the dinosaur's going to end up here, and the dinosaur ends up like further or nearer, or it's not the dinosaur, but like the cacti or whatever, right? So I think this is important. Oh, right. There's one other thing, right? Dealing with PPO training. Right. So remember when we use when we use PPO, PPO does a rollout about like when it does a rollout, it runs a bunch of episodes. Basically, it's running like so. In my case, it's running 4,096 steps, and then once it's done those 4,096, next steps, the end steps. That's what the end steps is. It just stops, but Dino carries on. He's gonna die, or she, and then like PPO is just like, oh, do some more steps in the existing episode, and like Dino's dead, right? And here again, Dino's already dead by this time. I mean, this is a fake environment here. Yeah, so we've got these gaps where PPO is not controlling anything. All it's doing is learning. It's just like, I'm going to go to sleep and dream about electric dinosaurs. Dealing with the FPO training, basically, if time since last frame more than 3 times 1/FPS, then assume PPO trained, set done to 1 and set reward to 0. There we go. The rest of the time, if Dino dies, reward is -1. If Dino doesn't die, reward is 0. Okay, so that works. That works really well. I should show you the training curve. I can't get the training curve on this computer because it's busy training. Well, I have a training curve from the video I took before, right? All right, so here's a training curve that I took with my camera while I was training. So here's a training curve. This is the one that I put into the video of the sneak peek of Dino 700. So yeah, it's just like until it hits birds and the white world, like the daytime, it just goes woo, straight up on this nice smooth curve. It's really nice. It's really smooth curve. It's great. It's just a straight line. And I ran it twice, right? Here was the first run. I like at this point, what happened at this point? I think I had to go to work and I was didn't feel like staying in my room and I didn't feel like just leaving my computer here. So I just turned it off and carried the computer with me. So yeah, and then so I ran again, and look, so they're both really similar curves. So the training's pretty good, and I hear it's when it hits the white world, and the white world's like the convolutional network's going to hate that white world because the convolutional neural networks had learned like the black background, white foreground, and now it's got white background, black foreground. It's just like oh, it's going to take forever to learn. So it's really not surprising to me it's gone down like this. Cool. All right. I think that's it. So one, two, three, four, five, six, seven innovations, right? And that gets score 700 in 6 hours on a MacBook Air. I admit that it's a MacBook Air M2, but it is technically a MacBook Air. All right. So I hope you enjoyed that. Please put any comments on like what you like, didn't like, what you want to do less of, more of, etc., etc. And I hope to see you in the next video. I mean, I hope you got this far. If you got this far, thanks very much. And yeah, I hope to see you in the next video.